Now again, don't change anything on your paper. Don't change anything on your paper, but go ahead and change the pear deck now that you've talked to your neighbors about it. What are you expecting to see? So waiting on a few friends to still include theirs in the mix. There we go. Max joins us. Come on. Aguirre, come on, Joshi. And again, if you're not in yet, it's XQGOP. Join us. All right. Here's what I'm seeing now. It looks like generally these are kind of curvy. Okay, the position graph is curved. This is a new thing. We saw this with the spinning thing going down the incline left. Curvy graph here, and then kind of a straight line, diagonal line graph here, and then acceleration graph. We don't really know what that looks like yet, but that's okay. It's curving. Okay. It's getting steeper. So can you share with us why you're saying that? Why did the position time graph get steeper? That's what I'm interested to hear right now. Why does the position time graph get steeper? Yes, ma'am. So why is position versus time getting steeper? Okay, in other words, people are drawing that graph to look like this. Why are you showing it getting steeper towards the end? Okay, what are we seeing here? Because the card starts from rest, so it's speeding up as it's going down the track. Because it moves down the ramp and increases speed because it's accelerating. Keeps rolling down the thing. Speed at which it's moving away from the motion detector is increasing. Okay, so it sounds like we've got some good agreement there on why we're drawing the shape of the graph that way. All right, let's not beat the dog here. See if I can do two jobs at once. So I've got the cart here by the detector. Donkey put his coffee in the way. I used to do this on the smart board, and now I'm remembering why. Just push the button. How'd we do?
You did good.
Curvy?
Great.
We've done good. All right. So there's a lot of stuff that's not the stuff we're looking for here. So let me change the time scale. And boop. Okay. So what are you thinking? Straight line or curvy line? Right? Clearly that's not a straight line. It's getting steeper. So I think we're pretty solid on our prediction for the position versus time graph. You already told me it's getting faster. Hey, what would you say about the steepness. What would you say about the slope of this graph as time goes on? So an important skill in graph recognition, okay, is to take a curve like this and kind of break it into chunks. So if you look here, right, this is why we did the secant thing the other day. So I'm kind of drawing, well, that's terrible. I'm kind of breaking this into chunks. What's happening to the slope of those chunks as we go on here? It's getting steeper. Remember that the steepness equates with how fast it's going. Because slope on the position versus time graph, that's our velocity. Okay? So let's look at the velocity time graph for the same window. And again, our kind of interest starts here at 1 second. We could really care less what's happening over here. So let's check it out. Velocity versus time graph. How'd we do?
We did great.
Did all right, yeah, on our predictions. Okay, so it's kind of looks like that. So this is what you're drawing on the right side of that first tile there on the sheet. The curve, the straight diagonal line of this. And then the other thing we're interested in is the acceleration versus time graph. Okay, and Hayden already talked to us about this. Okay, Hayden already talked to us about this. Acceleration is the slope on the velocity versus time graph. So take a moment with your neighbor. Hey, take a moment with your neighbor. And over on the Pear Deck, give me a couple words to describe the slope of this graph. Okay? What would you say about the slope of that graph? We got this thing called Pear Deck. You don't have to learn. You just type. So describe this slope in Le Pear Deck. Slope. Put our big important definitions over here. Oh yeah. Let's see what our friend said on the Pear Deck. Constant, positive slope, stays the same. Slope is constant. Constant and positive. Constant, consistent. Constant slope, straightish, line, yeah. Positive, not negative. Okay. Oh, is that a, what? How did Mr. Freeze say that word, lightities? Is anybody in AP English? Like it's where like you use the negative of the thing that it is. Well, it's certainly not negative to say that it's positive. No? Nobody? Lightities? Lightotes? Okay. Fair enough. All right. So that implies that so we said constant and positive. So the way that this thing works then, velocity is the slope on a position versus time graph. And acceleration is the slope on a velocity versus time graph. So I can just scratch out the word slope here and rewrite that as acceleration. Okay? So for acceleration, we're expecting to see something that has a constant positive value. Go ahead and sketch what you think that means on the left side of your sheet. If you have a constant positive acceleration, what does the graph look like? All right. Ooh, look at that. I'm going to change the value there. 2-ish. Okay. Would you call that constant? It's close enough for government work. Okay, that's what a horizontal line looks like in here. If I zoom out far enough, right, that's flat. Yeah. Okay, that's flat. There you go. So this is a constant positive acceleration. So go ahead and make sure you've got that on the right side there. Constant positive acceleration. Yeah, I should have dropped this in physics. Okay, so we've got that sorted out. Let's talk about the next section then. And in the next section, I've got to move. Let's see, I got to think about how this looks to you. So the detector stays on this end, but I'm going to flip the ramp. So that the detector is down at the bottom over here. And the cart's going to start out by the detector. I'm going to give it a push. Push. And then I'm going to pounce on it when it gets to the highest point there. Okay? So a push and a pounce. Think about what's happening here in terms of motion. Okay? It's interesting. Once it leaves my hand, push, pounce. Okay? So go ahead and draw that on the left side of your sheet. What's that going to look like for a position versus time graph? And once you thought about it, go ahead and draw that on the Pear Deck. Push and a pounce. Don't draw the push. Ignore the push. It's only interesting between the push and the pounce. If that works for you. Whoa, that's interesting. So again, once you've got it on paper, please go ahead and throw it onto the Pear Deck. Once you've made your prediction on the paper. Again, we're really only interested in it between when it leaves my hand until just before I pounce on it at the top. So you don't need to include what today is like after I've pounced on it. It ceases to be interesting at that point. Use your newfound understanding of acceleration to try to predict the acceleration graph this time. If acceleration is the slope on a velocity versus time graph, what do you expect to see here? based on the slope of the velocity time graph that you've just drawn. Still waiting on my friends to, get on task and stuff. Oh, but I can't just jack people with the Airzuka because maybe they're pair decking on their phone. Could that be? Helped your hair. It's all good. Ooh, but I can check on the pair deck. Join us, won't you? All right. Now there's some differences. Let's see if I can kind of pick those out. Big. Oh boy. Do I have all the differences? Big. I think so. All right. Pair deck. Don't grind my gears. Okay. So generally speaking, it looks like there's some agreement on the position versus time graph that it should go from close to zero to farther from zero. Okay? But how it does that, look at some of the different options we've got here. Actually, it's probably better if I do this. So here, I would class that as a straight diagonal line. There's kind of one of those types of curves. There's one of those types of curves. Oh, ghost graph. Okay. So ponder that with your neighbor. Okay. And sorry that's so teensy, but how should the position time graph go? Okay. Maybe I can give it an option over here. So I'm seeing some of this. I'm seeing some of, should we use different colors? Why not? I'm seeing some of this. I'm seeing, hey, buddy. Smartboard. All right. Freeze. That doesn't help, does it? Boop. There we go. So red, blue, green. What are you thinking? Run that by your neighbor really quick. You want to see it again? It looks like this. It's interesting after it leaves my hands. I push, and then it pounds. Okay. So what should be happening here in terms of graph slope? Chat with your neighbor. What should be happening to the slope based on the motion of the car? Maybe start with that. How would you describe the motion of the car? Constant? Is it getting faster? Is it getting slower? What should that do to the slope on the position time graph? If the velocity is increasing, if the velocity is decreasing. So I got too many screens going here. New question. Okay, let's just settle it this way. Velocity is increasing or decreasing? What do you think? Velocity increasing or decreasing? Sticking with the lie to tease. Well, it's not getting. All right, this looks pretty universal. Most people are able to agree that the velocity is decreasing. So keep in mind, based on our definitions, I can come in here and take that word velocity and replace it with the words slope on a position versus time graph. Okay, so this means when you draw your position versus time graph, the slope on position versus time should be decreasing. Is that what you have there? Double check that with your neighbor if you can get them back on task. And I'm gonna pop back over to here, okay, and make revisions on your pear deck. Are you showing a graph on position versus time that has a slope that is decreasing? What are you thinking, Mac fans? How do you draw that to show a slope that is decreasing? Max, let's get your position time graph in. Then you can do whatever you want to do. And let's see. So I would say we got this going for trends right now. Let's why do these have to take up such a small amount of screen space? Can I stack them? There we go. Okay. So here's what I'm seeing right now, friends. These are the three variations. I've just grabbed three of them. Which ones show a slope on the position versus time graph that is decreasing? How would you describe the slope of this line? It's negative, but it's a line. Is it getting steeper or flatter? It's not, right? It's a line. It's got the same slope everywhere. If I draw, dang it, should have frozen the screen, right? If I draw a secant there, or there, or there, or there, they're all going to have the same slope. I want to show a slope that is getting flatter. Okay, you should think of flatter as a synonym for decreasing here. So we end up with this then. That person has graciously dropped out. We end up with this type of a curve. That's a slope that's decreasing. What should the velocity versus time graph look like then? If your velocity, let's confirm quick that that's the correct position versus time graph. Let's see if we can get that. So position, all right, I gotta do this. Push, bounce, click, study for econ. How'd we do? What? Oh, okay. Thank you. How'd we do? I think we did all right. That looks okay-ish. Okay. So this is a position versus time graph. The slope of those things is decreasing. Okay? And we could just kind of flip around what we had just said previously. Velocity is the slope on a position versus time graph? You should be drawing a velocity that is decreasing in value. Here's the other thing you've got to ask yourself, though. If you look at this line segment here, positive, negative, or zero for the slope there. Is that a positive, negative, or zero slope? Run that by your neighbor real quick. Because that's going to clue you in on where should your velocity start. Should your velocity start at zero? Should it start positive? Should it start negative? That's based on the slope there. The slope at the end. So this last segment, would you describe that slope as positive, negative, or zero? That's going to tell you about your ending velocity. So pretty please talk to your neighbors, because there's a lot of variation out here right now in the velocity graphs. Parth, that's lovely use of color. Okay, my concern is that I'm still seeing this. I got velocity time graphs that look like that. I got velocity time graphs that look like that. But I'm thinking, based on our understanding that velocity is the slope on the position versus time graph, if you can identify if this is positive, negative, or zero slope, and if this is positive, negative, or zero slope, again, you can just drop in that word velocity or slope when we're talking about position versus time graphs. Okay, so let's take a sniff at it then. Velocity versus time graph, we're going to be interested in it from about there on. Boop, boop. So from about there on. So that means we're going to ignore this first bit here. What's going on here? What is this? This is big drastic feature of the graph. That is the what? The what? Thank you. The poosh. Okay. So here's the poosh. And then after the poosh, you can see it's going like that. I'm sorry, the axis is kind of obscured over here. This is 0, this is 1.0. So it's starting out positive and it's going to 0 here for the velocity versus time graph. All right, let's take a go at this slope then. How would you describe the slope? Slope is bop, bop, bop. So over on the pear deck, 1 or 2 words to describe the slope from the poosh to the pounce. From between, yeah, so this bit that I haven't scribbled on here. So if you look at this, if I hold a meter stick up to it, that slope is so I'm seeing constant and negative but constant, I think. Constant, decreasing, down, The slope at the push is increasing, but after a little bit, the slope starts decreasing until the pounce. Constant, negative, constant, constant, negative. Really steep, constant, and then positive, but then negative, and constant and less steep, steep. Negative from the push to the pounce. Constant, negative, negative. Okay? So I don't see anybody calling it a positive slope. We're clear on the fact that it's negative. But what we're unclear on is this notion of, is the slope constant? Is the slope decreasing? Is the slope increasing? Okay? So if I hold up a meter stick to it, and if it pretty much follows that meter stick, that's telling you that the slope up here is pretty similar to the slope right there, is pretty similar to the slope right there. So all those little line segments have pretty similar slopes. So if we flip this over to the acceleration graph, we see, wait, where's the graph, Anastasia? It's in the negative. Okay, let's try that. Hey, graph, where'd you go? Whoa. Whoa. It looks like a bat hanging upside down. Okay, so there's the push. And I just need to zoom out here. 0, -2, boop, something like that, okay? So the push happens, but then after the push, you've got a pretty constant, and hey, what's the value over here? -1. Constant negative acceleration. So I can go back over to the sheet. I can draw a position versus time graph that looks like that. I can draw a velocity versus time graph that starts out positive and goes to 0 like that. And I can draw an acceleration versus time graph that is constant and negative. All right. So I'd like you to at least register your prediction for this one. I'm going to have to put, the detector's going to stay at the bottom. What's going to change here is the cart starts at the top, and I'm going to let it roll towards the bottom, or right before it hits the detector. Oh, I'm going to pounce. So from the instant I let go of it until I pounce there at the end, what's the shape of those graphs going to look like? Go ahead and make your prediction on the sheet for tau 3. Get a moment, slap it into the paradigm. What is that even? So again, important things to be thinking about. Look at all the different graphs here. Whoa. That's not a happy view. Look at all the different graphs here. What's happening in terms of the motion? Is it getting faster, getting slower? So the velocity increasing or the velocity decreasing? Is it getting closer to the detector or farther away from the detector? Think about that too with the shape of your graph. Fastest when it's farthest from the detector or fastest when it's closest to the detector? All these different questions that kind of feed into this one. All right. And we'll pick up with this tomorrow.